Welcome everyone. Real quick, Zoom. Can anyone hear me? Nishant, are you able to hear me? Awesome, thank you. Okay. All right, so this session is on PyTorch and deep learning. If you intend to be in the machine learning, the intro to machine learning section, that is in Alder 103. And as always, if you realize partway through the session that you're in the wrong session, I won't be offended if you get up and leave. That's fine. Um, just to give you kind of a sense of where I'm going to start and what I'm going to assume you know in this session. So Ariel's going to talk about some things like cross-validation. If you don't know what cross-validation is, or if you've never done cross-validation, I might suggest you start in the machine learning section and then watch this session later. I'm going to kind of assume that you at least know what cross-validation is and why we have things like training sets and test sets. If you're pretty comfortable with that idea, you're probably fine. Um, uh, I'm uh, I'm also going to start out in a minute here by giving you a bunch of extra resources because honestly, this is an hour and a half session and I can't even teach you a little bit about PyTorch in an hour and a half. But I'm going to do my best. Okay. Um, Let me just get a show of hands. How many of you are at least, let me put it this way. How many of you have ever written an optimization loop? Okay, a good number of you. How many of you at least know what an optimization loop is or why you might need a loop in optimization? Okay, good. That gives me a lot more confidence about where I'm starting. All right. So, like I said, I'm going to start by giving you some resources because we really can't cover everything here today. So first of all, in the curriculum directory, I'm not actually going to open this, but on the hub, in the curriculum directory, there is a directory for Benson Pytorch, and there is a notebook in here. We're going to work through something similar to this notebook in the course today. I'm not going to actually open this and use it, but I'm going to just kind of live code, and we'll be working through something like this. This notebook is exactly what I went through in years past. So if you want to see a lecture of this notebook, go to last year or the year before, and you can see me giving a lecture on exactly this notebook. I'm changing things up a little bit this year because in past years, I've spent quite a bit of time talking about optimization before we talk about neural networks. And my assumption is that most of you here already know at least enough about optimization to be comfortable jumping right into neural networks. So that's what we're going to do this year. But if you want to see a little more about that, you can go to that notebook and you can look at past lectures. Additionally, there's this website, nben.net/AIABCs. This is actually a Jupyter book. This is a course I run during the year. And I'm pointing this out because it is sort of a treatment of machine learning in general. And there's four big sections, a section on unsupervised learning, a section on supervised learning, and then two sections, one on PyTorch and optimization and one on neural networks. We're going to kind of work through this section today in this lesson. But this is intended, this AIABC's course is intended as a very gentle introduction to machine learning. It's not full of theory, it's full of like attempts to give you intuition about how things work. So you might find this useful as a separate resource. And I will be referring to this just as a kind of reference occasionally during this talk here. Okay, in addition, you probably all are aware of this already, but PyTorch is one of these things, one of these libraries where it's so commonly used that language models are quite good at talking about it. So if you have now language models might not be the best place for you to start learning about it necessarily, but if you have questions about like how something works or why you're getting this weird error, language models are great at debugging PyTorch for those kinds of questions. But in addition, if you go to pytorch.org/tutorials, there are a whole bunch of additional tutorials here that cover just about every aspect of PyTorch. So, okay, I'm giving you all these right now. We're not going to actually use most of these in this lesson. I just want you to know about them as further reading. Okay, so with that kind of out of the way, I'm going to start by talking a little bit about neural networks, and I'm going to start with a couple visualizations here. So how many of you have used or written a neural network, let's say written a neural network in the past? Okay, several of you, actually. How many of you use PyTorch? How many of you use TensorFlow? Okay, So real quick, PyTorch and TensorFlow are two big libraries, the two main libraries for machine learning these days, especially for neural networks and convolutional neural networks. And they're very similar in terms of what they can do. In fact, I don't really think of them as being different in terms of their capabilities. But for whatever reason, well, there's a reason, PyTorch has become much more popular in academia than in industry. And TensorFlow has become much more popular in industry than in academia. And big picture, the reason for this is that PyTorch is very kind of loosey-goosey with how you do things. It lets you just kind of declare things and throw things around, kind of like working in Python. If you are familiar with Java, let's say, as a programming language, TensorFlow is more like Java. It requires you to say a lot of things just to get a simple thing done. But the plus side of saying all these things about what you're doing when you're writing your code is that you give the compiler and the debugger more power to catch errors. So it's harder to write wrong code in TensorFlow, but it's easier to write code in PyTorch. That's sort of a big picture difference. We're going to focus on PyTorch because it's what I've used, honestly, but also because it tends to be a little more common in academia and you can kind of jump in a little faster and get going with it. Okay, so artificial neural networks are a big topic, and convolutional neural networks are sort of the big technology that's taken the world by storm in the last 10 years. That's if you asked me 20 years ago whether I thought that by today we were going to have neural networks or any kind of algorithm where you could show it a picture and it could tell you what was in the picture, and that picture could just be like a natural image, not like some special picture it was trained on. I would think that I would have said 20 years ago that we were never going to be there by today. But convolutional neural networks in particular are the tool that has solved that problem. And so when I'm sure you've all heard of things like ImageNet and ResNets and these various kinds of neural networks. They're really good at looking at a picture, knowing that whether you show it a picture of a cat from the front or a cat from the side or a cat from the top or whatever, it can tell you that it's a cat. That's something that to me is kind of like a magical thing that happened during my lifetime. And the technology for that is deep learning or convolutional neural networks. But generally speaking, deep learning means any neural network that has more than one layer. So let's start a little more basic though. What is a neural network, and in particular, what is an artificial neuron? So I'm not going to read all this to you. I'm just going to show you the images here. But this is a diagram. I just got this off Wikipedia. This is nothing fancy. But not that Wikipedia isn't fancy. But I just got this off Wikipedia. This is a diagram of an artificial neuron, and sorry, Zoom, I will try to remember to use my mouse and not my hands. Okay, so the idea of an artificial neuron is that kind of like a real neuron, you've got axons that come in and dendrites that go out and connect to other neurons, and in the middle there's some kind of computation that happens. So what this diagram is representing is that we've got some number of inputs. These inputs are probably just numbers, like real numbers. So x1, x2, x3, these are just values that are going into the neuron, kind of like separate axons. Each axon or each input has a weight associated with it. And basically, we just multiply the input by the weight, and then we have what's called a transfer function. Usually, the transfer function is just that you make a weighted sum. So if we have 10 numbers here, we'll have 10 weights that go with each input to the neuron. We'll multiply each of those numbers that are inputs by the weight, and we'll add all those up, and we get some transfer value. We then have this activation function, and the simplest activation function is no activation function. The output of this neuron is just the weighted sum of the inputs. Okay, that's the simplest possible neuron. But realistically, we often use at least some kind of transfer function, activation function. And we'll talk a little bit more about that in a minute. But for now, just imagine we're doing some kind of transformation, like maybe a sigmoid transformation on the output. Anyone not know should I talk about sigmoids? Do we know what sigmoids are? Okay. So a sigmoid will take a real number and turn it into something between 0 and 1. I think of it as a real to probability converter. So a lot of times an activation function will be like a sigmoid function. So this is a pretty simple diagram of a neuron, and the output of this neuron may go to a bunch of other neurons, and that's where we get a neural network. So here's a diagram of a neural network. This is a pretty simple neural network, and the idea here is we've got this input layer is actually just the input numbers. So like this is x1, x2, x3, x4, and these are just real numbers that are the input to the network in this diagram. And each of these numbers goes into each of these neurons. So this cell here is like the first neuron in our network, and we can think of this circle as sort of encapsulating all of this, right? So each of these inputs has an arrow going into this circle. This circle has its own weights, and it comes up with a weighted sum, and maybe there's an activation function, and then it's got arrows going to all the neurons in the next layer. And so the information kind of goes from the input layer to each of these separately. Each of these separate neurons uses their own weights and potentially their own activation function, and they all send output into the next layer, and they send output to every neuron in the next layer. So far, so good. If I'm going too fast, or if anyone's confused, just please raise your hand and flag me down. Okay. So and here we have several layers in this network, right? So we're starting with just 4 inputs, and we're having it go to these 5 neurons and these 4 neurons and then these 3 neurons, and then eventually to a single output value. Okay. So let's imagine that this is our neural network. We put some numbers here. They kind of flow through. We get different outputs for every one of these arrows, and eventually we get a single output at the other end. Okay. Now let's imagine for just a moment that all of our neurons have no activation function. Okay. We're just using weighted sums in every neuron. So that's the simplest neural network we could kind of design. So what that means is we start with 4 numbers, and we produce 5 numbers by just using weights times the numbers. And this would be a little easier if I could write on a chalkboard or something, but essentially, we can think of this as a matrix multiplication. This step from this input layer to this first layer is a matrix multiplication. And the reason we can think of it that way, let me see if I can. Okay, I'm going to try to draw on my screen with my mouse. Bear with me. Okay, so suppose we have some input vector that's got x1, x2, x3, x4. I'm not going to try to write x. This is our input vector. It's just a column vector. If we have a matrix that is 4 columns and 5 rows, 1, 2, 3, 4, 5, then each of these rows gets multiplied by this column, and we get a value here, and then we get that for every one of these 5 rows. And that's basically weights times the inputs, and weights times the inputs, and weights times the inputs, right? Everyone understand how a matrix multiplication is equivalent to one of these steps if we don't have an activation function? Awesome. Okay. So in a sense, a very simple neural network is just a linear transformation, right? Matrix times vector is a linear transformation, so this is a simple linear transformation. And in fact, if we don't have any activation function in any of our neurons, then this step is a matrix multiplication, and this step is a matrix multiplication, and so is this one and this one and this one. And if you take a vector and if you take a matrix and multiply a vector by it, and then you have another matrix and you multiply that output vector by the matrix, and you have a whole bunch of these, what do you have? Like, come on, someone got this. You've got one matrix multiplication. Yeah, one matrix multiplication. So if you multiply 2 matrices together, you get a matrix. And if you multiply 4 matrices together, you get a matrix. So if there's no activation function in this network anywhere, then it's just a big matrix multiplication and it's nothing else. Okay? So the activation function is actually very important. Without it, you're just doing a linear operation. You may as well be doing linear regression. You'll probably get a better answer, or at least a faster answer. Okay, questions so far? All right. Thank you for bearing with my rambling about neural networks at the beginning. Okay. So I'm kind of debating in my head whether I want to. No, I'll wait and talk about convolutional neural networks when we get to them. Okay. At this point, I think let's start actually working with Pytorch and working with little data, and we'll work up to building an actual neural network, and then we'll go from there to convolutions. I think we'll have time. Okay. So you don't need to be in any particular directory. You can whatever. I'm just going to open up a new notebook, a new empty notebook here. And if you want to follow along, I'm just going to be live coding for most of this. So feel free to follow along with me. I will make this just a little bigger so it's easier to see. Okay. All right. So first thing we need to do is import Torch. Torch is the library name for Pytorch. When you install it, you install Pytorch, but then you import Torch. That's just the way it is. I'm gonna and to start out with, let's just start with this. I'm gonna import Torch. If you've never used Pytorch before, a good rule of thumb is that it's basically identical to NumPy with a bunch of little changes. So, for example, you can say something like torch.zeros. Whoops, if I can spell it right. .zeros. And I'm going to say I want a 3x2 matrix. If I run that, I get back a tensor instead of a NumPy array, but it's a tensor that's 3x2, just like we would expect with NumPy if we did np.zeros. Pytorch uses tensors instead of arrays, but for all intents and purposes, they're the same and they act very similarly. They're not actually the same, but they're very similar. And in fact, underneath the hood, Pytorch is just using NumPy arrays to store everything. So for example, let's suppose I say z equals torch.zeros 3, 2, and then I say z.numpy. It'll give me back an array that's equivalent to that matrix that we created. Okay, so let's suppose I say y equals z.numpy. And then I'm going to change something in this array. I'm going to say that z of 0, 0 equals 1. Then I'm going to print z. Sorry, I meant to change y. Suppose I get the NumPy array for the tensor, and then I change something in the NumPy array. And then I'm going to print out y, and then I'm going to print out z. Okay, so when we print out the NumPy array, we of course see that changed cell, right? And notably, NumPy arrays print out a little nicer than Pytorch tensors, but otherwise same idea here. But also when we print z, we notice that it's changed here too. And this is because underneath the hood, the tensor is just keeping track of a NumPy array. And when we asked for it and then changed it, it changed the actual tensor under the hood. So this is just to say that you can kind of convert pretty easily between tensors and arrays. And if you edit one, it'll change the other because they're sharing the same memory. Really, a tensor is kind of an array with some extra stuff built around it. Okay. Okay, so it's very easy to convert between NumPy and Pytorch. I'm going to import NumPy as np. And then I'm going to say a equals np.linspace 0, 1, 10. If you've never seen this function before, it gives you 10 linearly spaced numbers starting at 0 and ending at 1. So just to show you what that gives us, it's 10 evenly spaced numbers. And if we want to turn this into a tensor, we can say torch.from numpy of a. And that will give us back the exact same tensor. Notice again, it prints out a little bit differently, but fundamentally, it's very easy to convert back and forth. Okay, I think a lot of this is fairly obvious, so I'm not going to spend too much time on it. But big picture here, if there's a function you're looking for in Pytorch, it's probably the same function as in NumPy. So if, for example, you want to take the exponential function of that array we just created, in NumPy, we would say np.exp of a. Oops. In Pytorch, we can say the same thing, torch.exp. And here, well, I'll go ahead and pass it a. Torch.exp is the right function. This is going to give us an error, though, because it turns out that Pytorch really doesn't like to work with anything that's not a tensor. So NumPy is really flexible about this. If you give NumPy a list of numbers, it will just pretend like you gave it an array, and it will give you the sum back, or it'll give you the exponential back. So if we say np.exp of 1, 2, 3, it's totally fine with that. It knows these are numbers, and it'll just treat it as numbers. But when we did this with Pytorch and we passed it a NumPy array, even though Pytorch is using NumPy arrays under the hood, it still complains because it only wants to work with tensors. Part of this is to help prevent bugs where you accidentally pass the wrong thing around, but fundamentally, Pytorch is just a little more opinionated about this kind of stuff than NumPy is. So as a general rule, you have to turn things into tensors before you can use them in Pytorch functions. And so you can do that using the torch.tensor function if you have a list or something like that. you can turn it into a tensor with torch.tensor, kind of like numpy.array. There is no as_tensor function that matches the asArray function. Pytorch always wants you to kind of make copies, but ultimately they're fairly similar interfaces. Okay, questions so far? All right. So I won't go through all the functions that are similar between PyTorch and NumPy. It's most of them. Things like log and mean and sum and std and median and all that kind of stuff. It exists in PyTorch. It's pretty much the same interface. But if you have questions about a particular function or something, feel free to raise your hand or yell out, and I'm happy to answer. Okay, so one of the things that is very important about PyTorch is that PyTorch will automatically calculate derivatives for you. Now, I'm not going to spend too much time on this because I think it's a little bit tangential to what we care about in this course. But when you're doing optimization, almost all contemporary optimization involving real numbers is done using what's called gradient descent optimization. The idea here is that if you've got some function, like if I give you a function that I've written, but you don't know what's in the function, you can just call it to calculate the values. Despite having just the function and only being able to call it like that, you can still calculate a derivative because you can calculate the function at some point and the function at some point very close to it, and then estimate the derivative by just looking at the change over that small distance. When you have the derivative tells you which direction the function is increasing in. So if you're trying to find the minimum of a function, you just go the opposite direction. Or if you're trying to find the maximum of a function, you just follow the direction the derivative is pointing. And this generalizes to functions that have lots and lots of inputs, not just like f of x, but f of x, y, z, or f of x 1 through x 10,000. It doesn't matter. The multidimensional derivative, which we call the gradient, will always point in the direction that the function is increasing the fastest, and we can exploit that to figure out which direction we want to go to find the minimum of a function or the maximum of a function. If you are interested in this topic and you want to know a whole bunch more about it, we can have a breakout session about it next week. I'd be happy to talk about it, but that's about as much as I'm going to say about optimization for right now. So in NumPy, there's no good way to do this. You got to calculate those derivatives yourself, or you got to calculate them analytically. That's very difficult. PyTorch will, no matter how complicated your calculation is, as long as you perform it in PyTorch, PyTorch will keep track of the derivative and give it to you, no problem. However, that comes with some costs. And this basically these costs are that PyTorch is keeping track of all the calculations you're doing behind the scenes so that when you ask it for the derivative, it can go back and say, oh, you took the log and the derivative of the log is this. And then before that, you divided these two numbers and I know the derivative of those of division is this. And it goes back and calculates your derivative for you, but it has to keep track of this computation on the way. Okay, so let's just show a very quick example of that. Well, actually, no, I think we're pressed enough for time. I'm going to show you an example of that in a minute, but we'll keep moving for now. Okay, questions so far though? All right, either everyone's following or I've lost you already. Okay, but let's actually load in some data at this point. So what we're going to do for the rest of this session is we're going to load in a data set called the MNIST data set. Have any of you ever used the MNIST data set before? Yeah, okay. It's a very common tutorial data set. It's basically a collection of images of handwritten numbers. So like people writing like 5 with a pencil or whatever. And the goal we are going to have is to have a neural network or a convolutional neural network that can look at one of those images and tell us what digit is written down. Okay, so let's start by just loading in the data. So the data has been put on the hub already, so we can just say training images, comma, training labels equals torch.load. PyTorch can save and load any tensors or collections of tensors very straightforward. This is going to be in /home/Jovian/shared/data /Benson-deep learning /mnist_train.pt. And I'm going to pass one more option, which is weights only equals true. So this weights only option is basically saying if the file you're loading in tells you to execute some code, don't do that. It's kind of a security measure. Generally speaking, when you load things with Pytorch, you want to pass something like this because you don't want someone who's giving you a Pytorch that contains code to run without you knowing what's in it. Okay, we then have a test data set. We're going to say test images, test labels equals torch.load. And it's the same path, basically, home, Jovian, shared data, Benson, deep learning, mnist, test.pt. Weights only equals true. Okay. Okay, so I probably have a typo in my Benson deep learning test. Okay, so apparently it loaded the training data fine. Does anyone see a typo? Okay. The typo I had was that I had switched the I and the N here. Um, did anyone, is everyone able to load this? Okay, great. Okay, so what's in this? Well, let's just start by looking at these objects. So what's the type of our training images? It's tensor. No surprise there. We just loaded it in with torch.load. How about what's the shape? Just like with NumPy, we can ask for the training images.shape. And this is 60,000 by 28 by 28. So we might guess right off the bat that this is 60,000 28 by 28 images. And we can test that. Let's just, I'm going to import matplotlib.pyplot as PLT so that we can do a quick image plot. And I'm going to say plot.imshow. I'm just going to plot the first image. Training images 0. Okay, that looks like a handwritten digit, right? All right, I'll just so people can see what I did there. We just did a plot of the first image. If I pick out another image, it'll be another digit of some kind. I'm not sure what that's supposed to be. Probably a 5. Oops. Read that. Okay. Okay, what about training labels? What's the shape of it? Well, it's just 60,000. Okay. Um, sorry. Okay. So what about what type is it? Just like in NumPy, we can ask for the data type of the tensor. And this is telling us it's an int 64. So this is an integer. Let's just look at one. So training label 0 is 5. So that first image we plotted was a 5, right? Now, I don't know what this is supposed to be, so let's see what it is. Training labels of 100. Okay, that's a 5. This is a 5 too, apparently. I know, I wouldn't have guessed it. But okay. So what we have here is a set of a bunch of images and a set of numbers that are integers that go with that image. Okay, so we want to take these images and use them as training and test data for our neural network that we're going to build, right? And Pytorch has a bunch of opinions about how you organize your data sets and your data when you're doing training. And I'm just going to say up front that some of these assumptions that Pytorch makes about how you organize your data are not going to make a whole lot of sense necessarily. But I'm going to try to explain the justification behind them originally and why it works this way. So in our case, we're working with a pretty small data set for images. We've only got 60,000 images. That's pretty small for something like ImageNet. But although for those of us who study like subjects in MRI, it seems like a lot. But it's a pretty small data set for this kind of training project. Um, Typically, when you're training a CNN that does something like identify what's in an image, like ImageNet does, you've got a huge data set of images, and it's so big that you can't fit it in memory at once. And that's such a common paradigm in PyTorch and TensorFlow that they build it into the way that you deal with your data. So we're going to first set up what's called a dataset object, a Pytorch dataset. And what the dataset knows about is how many samples do we have in the dataset? And if we ask for one of those samples, it can get the sample back out for us. Okay. We're then going to create a data loader. And the data loader takes a data set. And the idea is that the data loader takes chunks of images and feeds them into the model during training. So it'll take however many images we can fit in memory, like maybe 1,000, maybe 10,000, depending on the image or whatever. In our case, we can fit them all in memory, but it'll take some chunk of them and it'll load them in and feed them into the model, and it'll shuffle the images during training so that we don't get the same order every time we run through them and that kind of stuff. But from the perspective of like, if you're used to using something like SciPy's fmin or something like that, this is going to feel like a lot of complexity we have to add. But it's because Pytorch is sort of organized around different assumptions about the way the data is organized. That said, writing a data set in a data loader is not that hard. It's just kind of unusual if you're not used to it. So we're going to start by saying class mnist data set. And we're going to look to have this class inherit from torch.utils.data.dataset with capital D. How many of you have never written a class before? Okay, this is no surprise. I'll try not to go on too much of a rant here, but basically PyTorch is an old language. It came about, God, I'm not even sure, 90s, 80s, 90s. It's been around for a long time. At the time it was written, object-oriented programming was kind of very in vogue. And these days, object-oriented programming is still around, but it's not nearly as in vogue. And basically, when Python was created, everything was going to be a class and an object, and everything fundamentally is a class and an object in Python. But it's sort of built around these object-oriented principles. So what does that mean? Well, classes are just types. The idea here is that a lot of times you have some chunk of data, and that chunk of data has a set of like native operations that go with it. So if I've got like an image, I might have a bunch of operations that have to do with like recoloring or getting a channel out or things that you do with images in general. And it's very handy to package those together. And that's what classes do, is they let you define a little bit of data and a little bit and some methods that go with the data. And you kind of get a data and operations that go together. And they're a nice way to organize certain kinds of code. We don't use them that much in academic science, in my experience, but they can be kind of useful. If you're totally confused by all of this that I'm about to write, I'd be happy to do a breakout session on object-oriented programming and other programming styles next week. But for now, just trust me that this is sort of a way of declaring a new type of object that can have some built-in operations. So this is if you are totally new to classes, this is all going to look a little arcane, and I apologize for that. I'll do my best to explain, but we're going to start by declaring a function inside of this class. Did someone have a question? Yeah.
I was wondering, because I've used fmin before, but I've never used this. Can you specify like how big you want your chunks to be as you iterate?
Yes. Yeah, absolutely. So that's called the batch size. And I'm going to talk a little more about this in just a minute when we get to the data loaders, but absolutely, we're gonna vary the batch size even. Cool. Yeah. Okay, other questions before I keep going? All right. So we're declaring this type called an mnist dataset. And the first thing we're going to declare is the function that gets run when you create the object. So you're creating a new mnist dataset. This function is the initialization function. And Python requires that this initialization function be called underscore underscore init underscore underscore. I'm not going to defend that choice of name. That is just what we have to work with in Python. The first argument is going to be self. So just real quick, anytime you see a double underscore on either side of a symbol like this in Python, that cues you in that this is like an internal Python kind of thing. This is part of like the Python language spec. They use double underscores to kind of, they call them dunder functions, or double underscore. They use these to like say this is the Python init function, as opposed to like the init function that I wrote for myself or something. So when Python has some built-in or low-level function, it's always got these double underscores. The self argument here is the object that's being created in the as you're initializing it. So when we create a new mnist dataset, Python allocates the memory for that dataset, and it's called self, and then it calls this init function with the self, the new object. And we're gonna, just as a preview here, we're gonna do something like obj equals mnist dataset, and we're gonna pass it our training images and our training labels. So we wanna create a particular data set. And these arguments are gonna get passed in to the init function as well after the self argument. So we're gonna have images and labels as the arguments to the init function. And we're just gonna store these as part of the object. So we're gonna say self.images equals images and self.labels equals labels. I'm additionally going to add something here. I'm going to say dot float. So this is a way, how many of you have heard of doubles versus floats? Does that ring a bell for people? Okay. So doubles are just floating point numbers. They're real numbers that are stored in memory that take up more memory, and so they can be more precise and bigger and smaller. Floating floats are the same thing. They just take up less memory, and so we have slightly less precision when we represent them. But for the kind of stuff we're doing, we don't need the precision of doubles, and it saves a lot of time and memory if we just use floats. And also, Pytorch really expects you to use floats for everything, and so we're just going to turn them into floats and make it easier on ourselves. Okay, that's our whole initialization function. I said that datasets need to know two things. One is how many samples there are in the dataset, and one is how to get a sample. So the next we're going to write a function called __len__. And this is going to take just the argument self. __len is the function that gets called when you call len on an object. So when you call like len of x, like if we call len of training labels, it gives us back 60,000. And what happens is it goes to the training labels object and it calls the len function if it's defined. So we just need to say the length of this object, the number of samples in this object is the length of self.labels, right? We got the labels and the images in. The length of the labels is the length of this is the number of samples. So that's all we need to return there. And that's our whole function. Last, we need to write a function that lets you get an item out of the data set, get one of the samples out. So we're going to call this _get item _. We're going to pass it self and item index. And we're going to return a tuple of self.images of item index and self.labels of item index. Oh, okay. And I forgot to close my tuple there, but otherwise I think that was fine. Yeah. Okay. Get item is just in a similar vein as like len is the function that calls length. Get item is what's called when you say training labels 10. It goes to training labels, finds the get item function and passes a 10. And that's how these work. Okay, big picture questions so far, or any questions really? All right. Okay, so we've created a data set type now, and we can go ahead. I'm going to use the same code here. I'm going to say train dset equals mnist data set of training images and training labels. And then I'm going to say test dset equals mnist data set of test images and test labels. And now, if we want to get a particular sample from our data set, we can say train dset 100, and it's going to give us back a tuple. Now, this is not a really pretty formatting, but it gives us back a tuple, the first element of which is a 28 by 28 image tensor, and the second element of which is all the way down here, the tensor 5, which is the digit represented. Okay, I'll leave this up here for just a second in case anyone is catching up with me. Okay, now at this point, we're going to need to make a data loader in just a minute here. Actually, let's do the data loader now. We're going to make a data loader. So I'm going to say train. Data loaders are a little easier. We don't have to define the type for data loader. Once we've defined the data set, the data loader class that exists in Pytorch can take over for us. Yeah.
Go up. Sorry, that's too.
Oh yeah, no problem. In fact, this cell is not worth keeping around. Just get rid of it. Okay. So data loaders are a little easier. We don't have to define the type. We've already done that for our data here. So I'm just going to say train dloader equals data loader. I don't remember if I imported that. We'll find out. Data loader train dsets. And then we're going to give it a batch size. So this is the question that came up earlier. Basically, we're saying, hey, data loader, we want to make a new data loader that is for this data set. And when we feed samples into the model, we're going to feed them in 60 samples at a time or 100 samples at a time or whatever. Yeah.
Sorry, this might be a dumb question, but why do we need the data loader if we already have our class that we can pull our data from?
Because this class, okay. There's a complicated answer here, or rather, there's two answers. First answer is we don't need the data loader. We could do all of this without it, but the fact is that you're almost always going to use a data loader in Pytorch, so I'm using it in this example. Secondly, if imagine we were doing this tutorial 10 years ago when your laptop had a fraction of the memory, you may not be able to store all these images in memory very easily, and you may need to load them in a chunk at a time. And so in that case, your dataset class here, instead of just taking the images and labels, might take a path where you've stored the data, and then when you ask for sample 10, it'll go load in sample 10 and give it back or something like that. And the data loader class manages all that and makes it so you don't have to worry about like finding just the right samples and shuffling and all that kind of stuff. It's kind of a convenience utility. Yeah. Good question, though. Okay, for batch size, I'm going to pick a fairly large batch size. I'm going to say 2,000 images at once. Now, batch size is a hyperparameter of the training, I'll say. If you're not sure what a hyperparameter is, big picture, it's anything that affects the training that isn't actually a parameter of the model. So like, for example, how big of a step you take during your gradient descent algorithm is a hyperparameter. The order you feed the images into the model is a hyperparameter. It's not a parameter that gets trained by the model, but it does affect how the training goes. So batch size is one of these. There's a lot to be said about hyperparameters, but I'm not going to talk very much about them in this lesson. Yeah.
Won't this depend on the RAM or how much data you have?
Yeah, absolutely. So so the question is, would this depend on the RAM? Yeah, if your data set doesn't fit in memory, and in fact, if only like a tenth of your data set fits in memory at once, you can't have a batch size bigger than a tenth of your data set. Yeah, so the data loader is going to load this many samples at once. Absolutely. Now we're loading all the samples right away to begin with, so this isn't like a big deal for us. But if you've got a really big data set or really big images, or like you're training on, so for example, suppose you're training on 3D MRI images. Those are 256 by 256 by 256 or thereabouts. That's a lot of memory just for one image. And if you've got like the whole Human Connectome project, 1,200 subjects, you probably can't fit those all in memory at once. So you would need to have a smaller batch size and have them fed into the model kind of one at a time or a few at a time. Yeah. Other questions? Yeah.
Does the batch size affect the training?
Yeah, so it is a hyperparameter if it affects the training. What you'll sometimes, so in theory, it shouldn't have a big effect on the final optimized model, in theory, but it can have a big effect on how quickly the model converges. So sometimes if you have like a really small batch size, it just may take a really long time to converge. That said, in my experience, batch size is not one of the big, like there's a lot of hyperparameters for any training. The learning rate you choose, which I'll talk about in a minute, which is like how big of a step do you take, that can have a huge effect. You can get vastly different answers based on your learning rate. The batch size, in my experience, does not usually change the output that much, but it is a hyperparameter. It's something you have to think about when you're training. Yeah. Other questions? Okay. So we're going to make this train data loader. We're also going to make a test data loader. And in this case, I'm actually going to say test dset, and then I'm going to say the batch size is equal to the length of our test dset. Now, the reason for this, there's a couple reasons I'm doing this. Usually your test data set is a lot smaller than your training data set. And when you're testing things, you don't care about shuffling the inputs and such. And so it often just makes sense to do the whole data set as one batch in your test data set. That said, you could put 2000 here and all the code that I'm about to write will work the same. It's just in this case, this will be fine. Okay, I'm gonna go ahead and run that. What's that? I didn't, and we can tell because we got an error. So yeah, I forgot to import the data loader. I believe I say from torch.utils.data import data loader. Yeah. So this is a utility that is packaged up with Pytorch. Okay, the way data loaders work, generally speaking, is you just iterate over them. And so we can say, for example, for inputs, let's say input image, comma, label in train deloader. And all I'm going to do here is print input image.shape and label.shape. Okay. Okay, so what we can see here is that every single every tuple that comes out of our data loader when we iterate over it is first 2000 images followed by 2000 numbers, which is kind of what we expect. So we're getting batches of image and numbers compost sort of, or image, yeah.
If you are not loading into memory the images from the beginning, you will get the path for a file that's called.
Okay, good question. Suppose we instead of giving images and labels here that we had already preloaded, we passed a file like a directory name, and we are going to load from that directory. So what would happen in that case is in our get item function here, we would say, oh, we need to get file path slash data file 10.pt or whatever, and we'll load that in, then return that, and that way we don't have to. That way by the time we're in the data loader, we're always getting objects like useful objects back. Does that make sense? Okay. Okay. I realized there's something I forgot here. So these are 2000 by 28 by 28, which makes total sense. Oh yeah, go ahead.
Is it data like an interval that can be exhausted? We already by
Yeah, great question. So is a data loader an iterable that can be exhausted? The way I interpret this is in you probably many of you have any of you used Scala, the programming language Scala? No, it was popular like 5 years ago. They distinguish between iterators that you could traverse once and iterators that you could traverse over and over and over again. I forget, they called it like a traversable if you could just go through it once and then you could never use it again. Data loaders are not traversables, they're iterables. So essentially if you iterate through a data loader, you can iterate through it again and it'll give you a new shuffled set of images. So every time you iterate through it, you get the images in a different order, but you can go through it multiple times and we're going to when we train. Yeah. Did that answer your question?
Yeah.
Okay. Okay. So it makes sense intuitively that we would have 2028 by 28 images, and you would think that this is what we would use to train. But there's another thing here that Pytorch assumes. So Pytorch assumes you're using images and that they have multiple channels like red, green, and blue, or red, green, blue, and alpha. And so Pytorch, even if you've got just a one-channel image like we do, it wants there to be a dimension after the batch size in the tensors you're using for training that represents the channel. And it wants that to be there even if you've only got one channel. And this is just like all of the Pytorch code we're going to use after this cell is going to make the assumption that you've got at least one dimension representing channels, and it has to be the dimension that comes after the batch size. I don't agree with this decision that Pytorch made, but it is the decision Pytorch made in their design. So we always, whenever we get data out of a data loader, we always have to have the first dimension of that data be the batch size. And the second dimension always has to be channels, even if your channel size is one. So what we need to do is we need to go back up to this data set object and we need to say, okay, we're going to load this particular item, but then we're going to put a none ... here. Have any of you seen this before, this weird syntax? Okay. This is in NumPy and in Pytorch. It's not specific to either, but let's suppose we have something like numpy.zeros 2, 3. Okay. That's a 2 by 3 matrix. And if we want to make it a 2 by 1 by 3 matrix, that's a kind of tricky operation, but you can say, I want all these dimensions, and then I'm going to put a none here, and then I'm going to put all those dimensions, and it'll insert a 1 dimension. Let me make this a little clearer. Wherever I put the none. So I could instead put colon none, and it'll give me 2 by 3 by 1. I could move this none to the beginning, and it'll give me 1 by 2 by 3. This is just a fast way to insert a singular dimension in the middle of your array, and it works for tensors or NumPy arrays. And so what I'm doing here is I'm saying, insert a singleton dimension representing the channels at the very front of this image array, and then the 28 by 28 dimensions comes after that. So if I run this and then redeclare my data sets and then redeclare my data loaders, and then I run this here, I now have everything as 2000 by 1 by 28 by 28. And now Pytorch will be ready to work with it. Okay, this is another example of Pytorch just having some opinions about how we organize things, and we just kind of have to follow them. All right, questions? Okay. Okay, I think we've kind of talked about enough stuff. Let's actually write a neural network now. So to write a neural network, we're going to do kind of what we did with the data loader. We're going to write a class, and it's going to inherit from a Pytorch type. So we're going to say class neural network, and it's going to inherit from torch.nn, which stands for neural network, .module. So the torch.nn.module type is a type that represents any model that you are using in Pytorch. Pytorch has its own notion of what a model is. A model takes inputs and produces an output, and they all inherit from this module class. I'm not sure why it's not the model class, but it is what it is. We're going to just have to define 2 functions in this class. The first is the init function, just like we did for the dataset class. And like with the dataset class, we're going to pass the self object as the first argument. And in this, for this model, we're just going to have the self argument. This neural network model is not going to take any optional arguments or anything. The first thing we have to do is we need to give the module type a chance to initialize itself and its data. So to do that, we use this call that goes super.__init__ like that. Super here, this super function stands for the superclass of the neural network, which is the module class. So this is a way of saying, hey, Python, go call my parents class to initialize the parent data as the first thing in the initialization of this object. This is kind of a common paradigm in object-oriented programming, because what we're doing is we're defining a new type that inherits all the functionality of this type. And so if that type needs some initialization, it needs a chance to initialize itself. Yeah.
This may be a weird thing analogy, but it looks a little like constructor in Java.
It looks a little like what?
It looks a little like a
The constructor in Java? Yeah. Okay, so yeah, this is the observation for those on Zoom is that this looks a little bit like a constructor in Java. If any of you use Java, this is exactly a constructor in Java, in fact. Yeah. And you even use the same terminology. You call the superclass in Java to initialize the superclass, and this is the same thing. Yeah. So if you're familiar with Java, Java is a super object-oriented programming language. Python is just a kind of object-oriented programming language. So if you're used to Java, these should all be kind of familiar. Yeah. Okay, so we're going to just declare a few things now. We're going to say self.flatten equals torch.nn.flatten. I will explain this in just a second. I'm just going to write this out first, though. Torch self.linear ReLU stack equals torch.nn.sequential. And then we're going to give it a series of operations that we want to perform on the data kind of in order. So like the way I'm going to think about this class or this neural network is that it's a filter where we're going to filter the data through layers of the neural networks and activation functions, or layers of neurons and activation functions. So when we have this torch.nn.sequential, what we're basically saying is we're going to put a sequence of operations or a sequence of models in order, and we want the data to just go from one through the next, and out the other end. So we're going to start with torch.nn.linear 28 times 28, 512. Linear is the name for one layer of a neural network. And the reason it's called linear is because of what we talked about earlier, where basically one operation from input to the first set of neural network nodes is a matrix multiplication. And a matrix multiplication is just a linear operator. What this model creates is a set of weights that will take an input that is 28 times 28 in length, and it will produce an output that is 512 values in length. So we're basically saying, start with the 28 by 28 pixels. This operator here is just going to flatten those 28 by 28 into a long vector. That's all that this operator is going to do. I actually could have put this in the sequential, not important. But basically, we're gonna start by flattening our input image from a 28 by 28 into just a vector of 28 by 28. We're then going to take those 28 by 28 sized vector, and we're going to do a matrix multiplication that creates a 512 size vector. We're then going to add an activation function, and the one we're going to use is called ReLU. How many people have heard of a ReLU? How many people could write the formula for a ReLU? Okay. Okay, it's real simple. ReLU is if x is less than or equal to 0, the output is 0. If x is greater than 0, the output is x. That is the whole ReLU function. So it is like a flat line and then an angled line, basically. So it's a real simple operator. It seems weird to me, just intuitively, that adding this operator makes much of a difference at all in the neural network, but actually it's very important. If we had time, I would do this multiple ways, and we could see that like without the ReLU, we get like no accuracy, and with the ReLU, we get a ton of accuracy. But long story short, the way I think of this, the ReLU changes the output based on whether it's greater than 0 or less than 0. And that kind of gives the neural network an opportunity to make like an if statement. Like if this is greater than 0, I'm going to go this way. And if it's less than 0, I'm going to go this way. And since weights can be positive or negative, you can use that to create a lot of different kinds of outputs. Long story short, you're adding a nonlinearity into your model. And once you have some nonlinearities in the model, you've got a much more powerful model than just a purely linear model. Okay, so this is just kind of one step, but we're going to add a few more, just a couple more. We're going to say torch.nn.linear 512 to 512. So this is just going to be an operation that goes from 512 size vector to another 512 size vector. We're then going to add a torch.nn.ReLU again. And then we're going to have one more torch.nn.linear 512, 10. Okay. The reason we're ending here with 10, so this clearly is going to start with a 28 by 28 input vector, and it's going to spit out a 10 element input vector. Now we're trying to predict a digit. So some of you might be going, well, that's weird. Shouldn't we be spitting out one number? And that's good intuition. But it turns out that it's, especially when you're trying to train a model to find an integer, it's actually really hard to get a model to learn to output something in this range. It's much easier to get a model to output 10 numbers and to make whatever number and to have each of those numbers correspond to one of your digits, and to have the model train the model to output a really big number for whatever digit it thinks is likely the correct answer, and really small numbers for all the other digits. I can't give you a very good explanation as to why that's so much harder, at least not in the amount of time we have. But you'll just have to trust me for now that this is a much easier approach, and you can kind of almost think of it as like we're training up 10 different neural networks that are very similar, and each one is just trained to say, is this a 1 or is this not a 1? Is this a 2 or is it not a 2? Is this a 3 or is it not a 3? That's a much easier problem to solve. Okay. Yeah.
So just a question of structure.
Uh-huh.
Input layer, a ReLU layer, which is the first hidden layer. So we have a linear layer, another hidden ReLU layer, and then the output layer. 3 hidden layers?
Hidden, I wouldn't call any of the, it depends on your definition of hidden. So I don't know that I have like a really strong prior as to what hidden means in this context. In like a hidden Markov model, for example, the hidden layers refer to things that you're not supposed to be observing above the surface. And so in the sense that it's not an input layer or an output layer, all these linears are hidden layers as well. Does that kind of answer your question?
Yeah.
Yeah.
I was thinking it's like, I'm just trying to understand how syntax relates to the layer structure.
Yeah, so
ReLU doesn't have any numbers for defining its size.
right. So ReLU will operate over every individual cell in the tensor that you give it, like separately. So if we give it 512 numbers as the input to the ReLU, it'll give us out 512 numbers and it'll do a ReLU on each individual number. So in fact, the way I would think about this is these two lines together form one step in the neural network because they are both the summation and then the activation. So the ReLU is the activation function that goes with this neuron. Yeah. So, sorry.
Started on 512 as being size for
no, I didn't have a good reason for picking 512. And in fact, I would encourage some of you to try a different number. You might get slightly different answers. 512 is big enough for this to work pretty well. But you know, there's kind of a fundamental question here. How much computation do you need to solve this problem? And if we increase this number, we add more computation. As with many things related to neural networks, it's kind of a black box and it's kind of an empirical question. I don't have a theory that will tell me, at least not easily, how many numbers I need in the middle of this neural network to get a good answer, but I can test it. I can try it with 512, I can try it with 1024, and I can keep increasing the number until it does well. Does that kind of answer your question? Yeah. Yeah. Do another 512? Yeah. So just think of it as a matrix multiplication. We've got a 512, our vector is 512 in size. The matrix is 512 by 512. And what this step of the operation does is it stores those 512 by 512 weights in the matrix. And those are what get updated during the training. So it learns weights that help solve the problem during the training. So it's a way of just like we're transforming a 512 length vector into a different 512 length vector using these weights that it learns. Now, if what you're asking is what is this layer supposed to do that solves the problem, I don't have an answer for that because neural networks are black boxes and it's going to come up with some set of linear equations that it then runs through a ReLU that works. But I couldn't tell you what it is. Does that answer your question? Each of these, yeah, so sorry, I haven't done a great job of explaining what these. So actually, let me hold that question and then I'll answer it after we do this next step. So right now we've just initialized a set of operations that can be run because we're still in the like the constructor, the initialization function. We now need to define another function called forward. And it's going to take, I'll just call it X. It's going to take the input. So this is the function that gets called when you run the model. When you give the model input and ask it to produce a prediction, it calls the forward function. And we're just going to write this out here. And actually, I made a mistake. This should be self, comma X, because this is a function in a class. So the object itself is always the first argument. So all we're going to do is we're going to say X equals self dot flatten X. So that's just, we're going to run this first step, which just takes the 28 by 28 and flattens that to a single dimension. And then we're going to say R equals self dot linear ReLU stack of X, and we're just going to return R. So when we give this model input and we ask it to produce a prediction, it's going to call this forward function and pass it X. We're going to pass X to this flatten operator, which is going to take whatever X is. And keep in mind, Pytorch wants everything to be batches by channels by whatever. And that's true of these models. So X is going to be a tensor whose first dimension is batches and whose second dimension is channels. And for us, that means it's going to be 2000 by 1 by 28 by 28. So that's the input is, and maybe I'll put that in the comment. X is 2000 batch by 1 channel by 28 by 28 image size. Okay, so what we do is we flatten X, and what this does, now flatten is a Pytorch operator, so it knows about batches and channels, and it's going to give us back 2000 X 1 X. What's 28 by 28? 784, thank you. It's going to give us back something this size because it knows about batches and channels, and it knows that when we flatten, we're just flattening that last dimension. And then we're going to take that output and pass it through this linear ReLU stack. And so this linear ReLU stack is a sequential set of operations. So it's going to just pass it through each of these in turn. So it's going to run this 784 sized input through this basically matrix multiplication and make it into a 512 size input. And then it's going to run the ReLU on it. And then it's going to run that ReLU'd 512 size vector through this next vector, or this next operator. And then it's going to ReLU that, and then it's going to do one more, and we'll get 10 outputs at the end. And so R here is going to be 2000 x1 x10. Okay, so far so good. Any questions? Yeah.
And the reason it's 2000 times 1 times 10 is because it's hard for it to do this just once, which is what we really would want, so we're gonna do it 10 times.
Right. So yeah, it just is harder to train networks to pick out a particular number on the number line than to train networks to be like, yeah, I think it's likely a 9 or not a 9. And so we trained it to 10 times, say either it's a 1 or not a 1, a 2 or not a 2, a 3 or not a 3 on 10 different channels.
And then you end up with some distribution of values that.
So let's think about it this way. The 2000 corresponds to our batch size. So we've given it 2000 images, and for each image we get back 10 numbers. And let's suppose the numbers are like, let's suppose that for digit 0, the number is like 10,000, and for digit 1 it's negative 50,000, and for digit 2 it's negative, and like they're all negative except also for 9, because 9s kind of look like zeros sometimes. 9 is like 20,000. Okay, so what the model is telling us in that case is it's pretty sure it's not a 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, but it's probably a 0 and it might be a 9. That's kind of what the model's saying. And we will just look across those 10 numbers and say, which of these is highest? And whatever one's highest is what we're going to take as the prediction. That makes sense? Okay. Okay. I think we've finally written our neural network. How much time do we have? Okay. We might not get through everything. Surprise. All right. Real quick, let's make a model. I'm going to say let's say model equals neural network. We didn't give it any arguments. The self argument is passed automatically, so we just make a neural network. And I'm just going to print the model. Notice that Pytorch has this nice way of printing things. It knows what we've built into the model here, and it shows all those steps. Okay, so at this point we are pretty much ready to train the model, and that's what we're going to do next. Yeah. What's the bias argument in the linear function? Yeah, so some of you may have noticed that linear has an optional argument called bias, and I believe you said it's true or false. And basically, that's the question. A linear layer can either learn just a matrix multiplication, or it can learn to do mx plus v, so that you have like an offset. And if you say the bias equal true, then it should train an offset as well as the matrix awaits. If you put bias equal true in here, it's not going to change the result very much, but feel free to try it. Yeah. Okay. All right. So, okay. I think we are ready to do some training. So, all right. There's a couple things we have not declared yet, but we'll discuss them pretty quickly. Usually what I do when we're going to write a training loop in this cell. And usually what I do when I write a training loop is I put my hyperparameters at the very top. So we're going to have a couple hyperparameters. The first is the batch size, which we already declared to be 2000. And in fact, I don't think we're going to need the batch size in this cell. I'm just going to put it here so I remember it. The next is the learning rate, and I'm going to pick a learning rate of 0.001. The learning rate, as I kind of alluded to earlier, is the question of how quick we're trying to learn. How big of a step do we take every time we do an optimization step? There's some really interesting dynamics here. If you pick a really small learning rate, everything will be fine. It just may take a really long time for you to find the minimum. If you pick a really big learning rate, things can go really wrong. So suppose we're trying to find the minimum of something simple like x squared, and our first initial guess as to the minimum is like 5. Okay, 5 is definitely wrong. And we look at 5 and we say, okay, the derivative is pointing in the positive direction, so we need to go in the negative direction to find the minimum. If we take a really big step, we might end up at -6. And now we're farther away from the minimum than we were when we started. And we're going to look at the derivative and we're going to say, oh, the derivative is pointing in the negative direction and it's even bigger. So we need to take a bigger step this time. And then we'll take another step in the other direction and we'll end up at like step +7. And we can end up going back and forth and getting farther and farther away from the minimum because our learning rate is too big. Once again, this is kind of an empirical thing. You pick a learning rate, you try it. If it goes off the rails, you pick a smaller one. If it takes too long, you pick a bigger one. I don't have really good advice on how to pick a learning rate exactly, but I often start with something around 0.01 or 0.001 and then multiply it or divide it by 10 until I've got something that works. We're just going to use 0.001 here for now. Okay, we need to declare a loss function. And this is one of the big kind of vocabulary things that I haven't mentioned yet, but essentially we're minimizing something, right? When we do this optimization, we need to minimize the error when we predict the handwritten image. So we're going to use that's called the loss function. The thing we're minimizing, the thing we want to have be as small as possible is our loss function. And long story short, our loss function is essentially going to be adding up for all of our images how wrong was every prediction. So if for every single image the output is always has the maximum value in whatever the correct digit is, our loss function should be very low. And if it's always predicting the wrong digit, our loss function should be very high. That's basically how this works. I wish I had a little more time to talk a little bit more about these because they are kind of important. Loss functions are basically assumptions about what kind of noise you have. There's someone asking a question. Okay. No. Sorry, was there someone online asking something? Okay, well, if there was, shut up. All right. So loss functions are basically you pick your loss function based on what you think the distribution of your noise is like. And in this case, because we're essentially predicting probabilities that each digit is the correct digit, we're going to use a function that's called the cross entropy loss. Like I said, this is we don't have time to talk too much about this, but the cross entropy loss is a loss function that is specifically for when you're trying to predict probabilities of categories, which is what we're doing right here. So I'm just going to say torch.nn.cross entropy loss. Torch has a cross entropy loss function built in, and so we don't really need to worry too much about this right here. Okay, one more thing we need to declare that we haven't talked about yet is the optimizer itself. There's a bunch of different optimization algorithms that are out there, but most of them are based on stochastic gradient descent or just gradient descent, and that's what we're going to use for now. We're going to say torch.optim.sgd, which stands for stochastic gradient descent. This isn't actually a stochastic algorithm. It's a gradient descent that's designed to work well when you're getting shuffled images as your inputs. So essentially, that's why it's called stochastic, is because it could be stochastically shuffled. But it's just a gradient descent algorithm. We have to tell it what the parameters are that we're optimizing over, because it has to know what parameters to update every step of the optimization. But fortunately, Pytorch keeps track of this for us, and we can just say, hey, we've declared our model. We declared it up here. Actually, I'm gonna declare our model right here as well, just to be explicit. So we've got our model. We can just ask it what the parameters are, and Pytorch already knows this because we inherited from that module class, and it knows about parameters. Okay, we also have to tell the optimizer our learning rate. So I'm just going to pass it LR equals LR here. We've declared the learning rate up here. Okay, we're finally ready to write the loop. So for batch num, comma, X, I'm going to do capital X and lowercase y because X is a set of tensors and Y is a set of digits. In enumerate train deloader. So if you haven't seen enumerate before, it iterates over something, but it gives you back a tuple of like 0 in the first element, and then 1 in the first element, and 2 in the first element. So this is the way I get the batch number to come along with the input and the label here. Okay, this is the loop is actually not that complicated. We're just going to say the prediction is equal to model of X of our input. Our loss is equal to the loss function of our prediction versus this Y, which I often call this the gold standard or the gold. So a lot of times people call this the true value, or like you've got your input and your true value, and you're trying to predict the true value. I don't really like that because there's usually noise even in these kinds of measurements, there are noise. And so they're not really true values. And so I often call them the gold values. They're like the gold standard values. Regardless, whatever you call it, you pass it to the loss function here. This loss function computes the loss of our prediction versus our true digit. And then we're going to tell oh, and I actually forgot a step here. We always start by telling the optimizer, we have to tell the optimizer that we're starting a new step. And we do that by saying 0 grad. 0 grad isn't a really descriptive name for this, but it basically is saying, hey, we're starting a new step. Whatever you've been keeping track of regarding the derivatives, forget all that. Zero it out because we're starting over. So that's why we say 0 grad. And then we say loss dot backward. I'll explain that in just a second. And then optimizer dot step. Okay. Optimizer.step is kind of self-explanatory. Once we've calculated our loss, we want the optimizer to look at the derivative and take a little step that improves the model a little bit. This loss.backward is kind of a weird one. It's called loss.backward because the algorithm for calculating gradients is called the backward gradient propagation algorithm. And the idea is that Pytorch keeps track of this graph of all the computations you've done to compute this value, this tensor loss. And when we say loss.backward, it says, oh, I can start from loss and go backward to the original parameters you used and calculate the gradients of the loss in terms of all those parameters using this graph that I kept track of. That's why it's called backward. But really, you could call this calculate gradients. That would be the same idea. So essentially, we're telling the optimizer we start a step. We have the model predict a value from our inputs. We calculate what the loss is based on the value we predicted. And then we say, go calculate the gradients of the derivatives of the loss, and then have the optimizer take a step. The last thing I'm going to do here is I'm going to say, I'm just going to have it print, I'm going to have it print loss colon, actually, I'm just going to make this a little simpler. loss, I'm going to say float of loss.detach, and I will explain that in a second as well. And then, no, that's fine. We'll just print the loss. Okay. Float of loss.detach here. I didn't really talk about detach. We didn't have a lot of time, but when you're calculating gradients for things, and you ask for Pytorch to turn something into a floating point number or a NumPy array, it complains because it's still tracking all this stuff about the gradients and it doesn't want to forget that. When you say loss.detach, that's a way of suppressing that error basically. So we're adding this here. Normally I would just say float of loss, but because loss is part of this gradient calculation, I'm detaching it from the gradient graph and then calculating it. Okay, let's see if this runs. Okay, shoot. It's very easy to have a typo or something in here that causes everything to go haywire. So I'm glad to see that ran. So hopefully what you can see right away is that initially our loss is very high. Now 14 doesn't mean anything to me in particular. And this is often the case for loss functions. Your loss function is going to be higher if you have more samples in your batch because you're calculating the loss over more things. Your loss function may be higher because the minimum loss you can obtain with the loss function you gave it is like 1 or something like that. Like the loss doesn't have to have any specific meaning. It just needs to be it just needs to be the case that when the loss is smaller, the model is better. That's all that really matters here. And hopefully you can see right away that the loss is getting smaller pretty quickly. And right away we've got almost no loss, pretty low loss compared to where we started. So it looks at least like this is working okay. So let's just test it out. We've now trained our model. Our model is ready to be run, essentially. So what I'm going to do here is I'm going to grab an image and a label from our test data set. The important thing about the test data set is that we just trained this using the training data set. It's never seen the examples in the test data set at all. We didn't use the test data set anywhere here. We just used the training data loader. So so this test data is all independent. As a reminder, whoops, I need to give it like I'll just take the 10th item here. Our image.shape is 1 by 28 by 28. And when we pass this to our model, yeah. Sorry? Do we have to call the forward function? Yeah, good question. So unintuitively, we never call the forward function because this call right here calls it for us. So calling model of X is a shortcut for calling model.forward of X, basically. Sorry, I'm having trouble hearing you. Exactly. Yeah, you need to write the init function and the forward function in your model, right? Okay. All right, so we've got this image. It's channels by 28 by 28. If we just pull out one example, so obviously, if we want to pass this to our model, which requires a batch size, we need to give it a batch size of none, and we can do that by using this none trick once again. But let me go ahead and say pred label equals model of im none comma dot dot dot, and then we'll just print the pred label. So, okay, we ran our model and we got out a predicted label, and notice this is just a bunch of numbers. And the biggest number is this one, is 0. So it seems to think that for this particular example, that this is a 0. And we can run torch.argmax, and it'll tell us that everyone know what argmax is, or anyone not know what argmax is? Yeah, okay. So torch.max gives you the maximum value in a list. Torch.argmax tells you the index of the maximum value in the list. So when we say what's the argmax of pred label, it says 0 because and actually since pred label has batches as its first dimension, I should have called pred label 0, but it's the same answer in this case. So right, pred label 0 is the vector we want to look for the maximum of, and in this case, it's the 0th element. So the model is predicting that this image is a 0, and now right at the end of the course, we're going to see if our network actually worked by printing out this image and seeing how it looks. So the image I extracted is called im, and I'm going to, since we have this extra channel dimension, I'm going to say im of 0. Oh, good. Okay, it is a 0. And just to kind of demonstrate that this isn't, I'll just pull out another one. And in this case, it's a 3, and it thinks it's a 3. So, okay, we've trained a neural network. That was a pretty simple neural network that seems to be able to recognize these digits without any trouble. And unfortunately, I was next going to just talk about convolutional neural networks, and we were going to update this neural network model we wrote to be convolutional. I don't think we have time to do that, but I'm going to real quick just give you a very high level overview of what a convolutional neural network is and how it's different. Hopefully this just takes a couple minutes. Okay. Neural networks are inspired by actual neurons. Convolutional neural networks are inspired by the visual system. First order of business is, what is a convolution? This image you're seeing right here is showing you the steps in performing a convolution. you've got a big image, like this is your image here, like our digit image. And this little matrix is called a kernel. And the idea is we slide that kernel along the big image, and at every point where they overlap, or at every alignment point, we multiply all the elements in the kernel by the overlapping elements in the big image. We add them up, and that becomes this cell of the output matrix. And then we move it over and we do the same thing, and we move it over and we do the same thing, and then we move it down and across. And basically, this is a way of kind of saying, what's the overlap, or like describe the overlap of this little matrix with this part of the image and this part of the image and this part of the image. Is this fairly clear to people? Okay. So this is mathematically what an image convolution is, but I think a slightly more useful intuition is to look at some examples. So this is a black and white version of a kind of famous painting by Andrew Wyeth. And I picked it because there's a lot of blades of grass in here and they're very vertical. And in a sense, as a vision scientist, I look at this and say there's a lot of vertical energy in this picture. If we take a kernel like this is kind of like a really low resolution Gaussian. It's a little bit like a mound. What we're doing is we're taking little neighborhoods of the image and we're kind of averaging them all together, all the pixels in that neighborhood together when we do a convolution. And it's probably, I'm guessing you can't tell on the projector, but this is just a slightly blurry version of this image. And that's because we're blurring it by merging pixels that are close to each other together using this kernel. This kernel, on the other hand, is high in the middle and is low everywhere around it. So it really, it produces a large value when there's a pixel where that's very different from everything around it. And so it sort of like highlights differences. You can see the blades of grass a little more clearly in this image, although again, it's a little hard to see on this projector. These two images are maybe better examples. Here we have like a vertical line surrounded by lower level vertical lines. So if we have a light vertical feature in an image next to a dark vertical feature, this matrix is going to produce a really big number. And we get these vertical, we see all the vertical energy in the image as the output. On the other hand, if we do a horizontal convolution, we can extract all the horizontal energy, and you can see that very clearly in the horizon here. Does that kind of make sense intuitively, at least what's going on? So in a sense, what these convolutions are doing is they're sort of pooling over little bits of the image and extracting certain kinds of features, like a filter. And if you do a bunch of these in sequence, you're sort of pooling over bigger and bigger parts of the image. And here we're using very small kernels, but kernels can be quite a bit larger. They can be like 7 by 7 or much bigger. And the idea is that you can sort of transform the image through a set of filters until you have something that's very useful for whatever computation you're doing. This is very similar, if you're not a vision scientist, this is very similar to how the visual system works. Even in the retina, we have, like, these are very inspired by circuits in the retina that you have that extract horizontal or vertical information, that extract information at different spatial frequencies. And by using these convolution kernels, you can extract that kind of energy from images. And that kind of stuff is very useful for identifying what's in an image or segmenting an image or that kind of thing. Shoot, there was one more thing I was going to say, but I lost my train of thought. Just to give you a sneak peek, if you go through the notebook that's in the curriculum folder, there is a convolutional neural network training. There's also a convolutional neural network code in this AI ABCs lecture. If you go through all that code, you're going to find that the neural network we just trained is about as good as a convolutional neural network. The difference is the convolutional neural network has these little kernels as their parameters, whereas our neural network had this great big matrix so like in our neural network, we had a 512 by 512 matrix. That's a huge number of parameters, thousands and thousands of parameters that are being learned for that one operation. In this convolution kernel, there's only 9 parameters, and we're just sliding it along the image. So convolution is a really efficient way to extract information from images. And that's kind of what's special about it compared to other more traditional neural networks. So if you have a 300 megabyte convolutional model, that can do a lot more than a 300 megabyte neural network model. The model we just trained is probably 3 megabytes. A 3 megabyte convolutional model will be able to do a lot more than that. Sorry, we didn't get to train a convolutional model, but we're out of time. I hope this was useful for everyone, and you maybe at least learned a little bit about how PyTorch thinks about things. PyTorch is a really powerful tool. I encourage you to look at other resources and stuff. And if you're interested in using it next week, I'm around and happy to answer questions. All right, thanks everyone.